Hello. I have a big lesson for you today. It's long, it's important, and I need you to be really engaged both in your mind and body. So if you need to, go grab maybe a Coke and some popcorn or coffee and a muffin. Today, our learning objective is to use derivatives to find where a graph is concave up or concave down. Sounds simple enough, but there's so much to it. You've already seen that locating the intervals on which a function f increases or decreases helps describe its graph. We can also look at when f prime, the slope, is increasing or decreasing, which will tell us if the graph of f is concave up or concave down. Now notice we can be looking at when f is increasing or decreasing, or when f prime, its slope, is increasing or decreasing. So keep that in mind. The definition of concavity: let f be differentiable on an open interval I. The graph of f is concave up if f prime is increasing and concave down if f prime is decreasing. Let me show you what that looks like. So I have two graphs here. The first one is concave up. The second one is concave down. And on the first one, I'm going to put little tangent lines on each of those points. And when I put the tangent lines on, think about what the slope of each of the tangent lines is, okay? So first one, we've got a negative slope. And then on the next point, it becomes positive. And then it becomes more positive, and then even more positive. So the slopes are increasing in value, and the tangent lines lie below the graph of f. That's for a concave up graph. Now let's look at the concave down graph. Again, at each of these points, let's put a tangent line and see what's happening to the slope of the tangent lines. So the first tangent line is positive, and then it goes negative, and then more negative, and then more negative. The slopes are decreasing in value, and the tangent lines lie above the graph of f. The derivative of f is f prime. F prime shows us where the graph of f is increasing or decreasing. At the zeros of f prime, the graph of f may change from increasing to decreasing. The derivative of f prime is f double prime. F double prime shows us where the graph of f is concave up or concave down. At the zeros of f double prime, the graph of f may change from concave up to concave down. Given f of x equals 1/3 x cubed minus x, determine the open intervals on which the graph is concave up or concave down. First thing is we need to take the derivative. And if we're looking for a concavity, we need to take the second derivative. And we're going to set the second derivative equal to 0 and solve for x. X equals 0. And like we did last lesson in the first derivative test, we're going to use a little picket fence or a number line to help us organize the information. On the top, I'm going to keep track of what f double prime is doing, and on the bottom, I'm going to keep track of what our graph f is doing. I have a critical point, or 0, at 0. And anything to the left of that critical point on f double prime is negative. Anything to the right of 0 is positive, which means on my actual graph, on the parent graph, anything to the left of 0 is concave down, and anything to the right of 0 is concave up. Now, if we need to explain that, because remember, that is not a justification in and of itself, we would say f of x is concave down on negative infinity to 0 because f double prime is below 0 or f double prime is negative. F of x is concave up from 0 to infinity because f double prime is greater than 0 or positive. Now that point where the graph of f changes from concave up to concave down is called an inflection point. Points of inflection. Let f be a function that's continuous on an open interval and let c be a point on the interval. If the graph of f has a tangent line at this point, then this point is a point of inflection of the graph of f. If the concavity of f changes from upward to downward or from downward to upward at that point. You could also think about it like this. If a point is a point of inflection of the graph of f, then we either have f double prime equaling 0 or f double prime is undefined. Okay, we're going back to our graph, 1/3 x cubed minus x. And what we're going to do is compare the graphs of f, f prime, and f double prime to see what f prime and f double prime tell us about the graph of f. So we're going to start with our picket fence. On our picket fence, we'll be keeping track of f prime on the top and f on the bottom. You can see from my graph of f prime that I have two critical points or two zeros. One of them is at -1 and the other is at 1. To the left of -1, my derivative graph is above the x-axis. That means it's positive. That means my parent graph is increasing. Then when it gets to -1, the graph turns around, okay? So notice the 0 on the derivative graph is where my parent graph turns around. Between -1 and 1, my derivative graph is below the x-axis. It's negative, which means my parent graph is decreasing. And then at 1, it turns around again. So again, this turnaround point is the same as the 0 on the derivative graph. And then anything greater than 1, my derivative graph is above the x-axis. That's positive, so my parent graph is increasing. Let's bring in the second derivative graph. So we have f double prime is 2x, and we've already worked with that a little bit. We'll bring up our picket fence again. On the top, we're keeping track of f double prime. On the bottom, we're keeping track of our parent graph. And like before, we can see that there is a critical point or a 0 at 0. Anything to the left of 0 is below the x-axis, that's negative, which means my parent graph is concave down. Then at 0, the concavity, look at the parent graph, the concavity changes from concave down to concave up. Now, anything to the right of 0 is above the x-axis. That's positive, which means my graph is concave up. One more layer that I want to talk about here, and that's the relationship between the f double prime graph and just the f prime graph. The f double prime graph has that critical point at 0, but how does that tell us about the f prime graph? Well, again, f double prime is below the x-axis to the left of 0. That's negative, which means that f prime is decreasing. The slope of f prime is negative. And then to the right of 0, our double prime is above the x-axis, it's positive, which means f prime is increasing. the slope of f prime is positive. In the example we just did, the function is continuous on the entire real number line. However, if a function is not continuous, then the x values at which there's a discontinuity, along with the values of f double prime equaling 0 or where f double prime doesn't exist, those should form the test intervals. New problem. And I'm going to go through the derivatives pretty quickly. If you want to pause the video and work out the derivatives on your own, that's great. But I'm just going to tell you what they are so we can see the big picture of what's going on. Determine the open intervals on which the graph of f of x, which is x squared plus 1 over x squared minus 4, is concave up or concave down. The first derivative is negative 10x over x squared minus 4 squared. And the double derivative is 10 times the quantity 3x squared plus 4 over the quantity x squared minus 4 cubed. So we're curious about the critical values of our f double prime. Are there zeros? Well, actually there's no point at which our double prime graph can equal 0. The top is just always going to be positive because of this x squared. But at x equals plus or negative 2, that's looking at the bottom, the function is not continuous. So if we get our picket fence going on, f double prime on the top, parent graph of f on the bottom, we have our negative 2, positive 2 critical points that we got from the denominator. If we plug in a test point less than negative 2, we would get a positive f double prime. Between negative 2 and 2 is negative, and greater than negative 2 is positive. So we have concave up, concave down, concave up. There are no points of inflection on this graph. And I wanted you to see that there are critical points, but those critical points are actually those vertical asymptotes. Determine any points of inflection and discuss the concavity of the graph of f of x equals x to the 4th minus 4x cubed. First derivative is 4x cubed minus 12x squared. Second derivative is 12x squared minus 24x. We'll set that equal to 0. Find the zeros of that, which are going to be 0 and 2. Time for our picket fence. 2 critical values. And I just threw some test points up here for myself. So if I plug in negative 1 to the second derivative, I get a positive number. I don't care what the number is. I just care if it's positive or negative. If I plug in 1 to the second derivative, I get a negative number. And if I plug in 3, I get a positive number. So we have a concave up graph, and then it goes to concave down, and then switches to concave up again. F is continuous on all real numbers. The points of inflection occur at f of 0 equals 0. So I can just plug this 0 back into the original function to find exactly where the inflection point is. And at f of 2 equals negative 16. F of x is concave down on 0 to 2, that's in the middle here, because f double prime of x is negative, and f of x is concave up from negative infinity to 0 and 2 to infinity because f double prime is positive. So there's the graph of that one, and you can see, let's put the points of inflection in there. At 0, 0, it changes from concave up to concave down, and then at 2, negative 16, it changes from concave down to concave up. Example 4, find the inflection points and the open intervals of concavity of the function 1/2 x plus sine x between 0 and 2 pi. First derivative is 1/2 plus cosine x. Second derivative is negative sine x. Where is negative sine x 0? Well, at pi. We're also going to keep in mind that we have endpoints on this one, 0 and 2 pi. And now we can put some test intervals in here. So between 0 and pi, negative sine x is negative. Between pi and 2 pi, negative sine x is positive. So we're concave down, and then we're concave up. Because f of x is continuous on the interval 0 to 2 pi, we do have a point of inflection at pi over 2, because our double derivative changes sign at x equals pi. G of x is concave down from 0 to pi because g double prime is less than 0, and g of x is concave up from pi to 2 pi because the double derivative is greater than 0. Example 5 says use a calculator to find how many times the graph of x squared minus 3 plus sine of 2x minus 1 changes concavity between 0 and 2 pi. I'm glad this is a calculator question. So we can find the first derivative, which is 2x plus 2 cosine 2x minus 1. We can find the second derivative, which is 2 minus 4 sine 2x minus 1. Then, this is where the calculator comes in really handy. Just graph it and count how many zeros there are. 1, 2, 3, 4. The graph changes concavity at each of these zeros. In addition to testing for concavity, the second derivative can be used to perform a simple test for relative maxima and minima. Let f be a function such that f prime of c is 0. We have a critical point in the first derivative, and the second derivative of f exists on the open interval. If the second derivative is greater than 0, then that means it's concave up, and that means our graph has a relative minimum. If the second derivative is negative, it's concave down, and that'll give us a relative maximum. All right, so let's go ahead and use the second derivative test to find the relative extrema of a couple functions. So here we have a polynomial, x to the fourth minus 4x cubed minus 2x squared plus 2x. First thing we're going to do is find the critical points of the first derivative. That's where the graph is going to be turning around, where the slope of the parent function is 0. So there's my derivative, and if I clean that up a little bit, I can divide out some 4s and then do some factor by grouping. Do you guys remember how to do that? And then set it equal to 0, and here we have the critical values of the first derivative, -1, 1, and 3. Now, what I want to know is, what's the concavity at those points? And concavity lives in the second derivative. So let's take the second derivative. We get 3x squared minus 6x minus 1, and we're going to plug in each of the critical points of the first derivative. So g double prime of -1 is 8. Well, what does that mean? That's a positive number, and a positive number means that we have a concave up graph. And if you have a concave up graph, then where the slope is 0, that's a minimum. Okay, so the next one, let's clean this up. We'll do the second derivative at 1 is -4. That's a negative, that's concave down. So where the graph turns around, where the slope is 0, that's what the critical point tells us, that the slope is 0, that's going to be at the top of that concavity, so that's going to be a maximum. And then finally, the last one, the double prime at 1, that's another positive one, so it's concave up, giving us a minimum. And there's the graph, so you can just, double check my math. At -1, concave up is a minimum. At 1, concave down is a maximum. And at 3, concave up is another minimum. Okay, what about this one? X to the 4th minus 2x cubed minus 3. Again, let's find the critical points of the first derivative. So first derivative is 4x cubed minus 6x squared. And we'll do a little bit of factoring. And we get x equals 0 or 3/2. Now this one gets interesting. So let's go ahead and pull the graph up here. We've got our two critical points of 0 and 3/2. Now what's happening at those moments? Well, let's find the second derivative, 12x squared minus 12x. And if you plug in 0 to that, you get 0. So at 0, the sign of g double prime, it's neither positive or negative. So is it a maximum or a minimum? Well, it's neither, because you can see at 0, it just kind of flattens out and then keeps going. But if I plug in 3/2 to the double derivative, I get 9. That's positive, which means the graph is concave up. Indeed, it is. And so that there would be a minimum. In the table at the right, we've got selected values for g of x, g prime of x, and g double prime of x. The function g of x is a twice differentiable function. That's important. And it's continuous on -4 to 5. Explain why there must be a value x equals c on -4, 5 such that g of 7 equals 7. Okie dokie. Well, what's happening at g of -4? We're at 0. And at g of 5, we're at 8. So this would be the intermediate value theorem, because since we start at 0 and end up at 8, somewhere between there must be a 7. Does g of x have a local maximum, a local minimum, or neither at x equals 3? So at x equals 3, here's some of the information we know. We know that the first derivative at 3 is 0. That's a critical point of the first derivative. And we know that the double derivative at 3 is -2. That's a negative number. That means we have a concave down graph. Therefore, this spot right here, which is the point 3, 4, is a local maximum. The graph of f prime, the derivative of a function, is shown. On what open intervals is f increasing? Okay, actually, before we answer any of the questions, we're just going to analyze this graph. First of all, it's very important to know that this is the derivative graph. And it's going to be really helpful to just start with our picket fences to organize our brain. So the first picket fence, I'm going to be keeping track of f prime on the top and the graph of f on the bottom. And f prime has 3 zeros at A, B, and C. And just looking at the graph of f prime, I can see that to the left of A, it's above the x-axis, it's positive. Between A and B, it dips below the x-axis, it's negative. Between B and C, it's positive. And then anything to the right of C is negative again. So what does that tell us about our parent graph? That it goes from increasing to decreasing, increasing to decreasing. Now, let's think about our f double prime. We'll keep track of f double prime on top, the parent graph on the bottom. How do we figure out anything about f double prime? Well, f double prime is the derivative of f prime, which means it's the slope of f prime. So look at the graph of f prime, and the slope is negative. And then at x equals -1, it turns around, and then the slope is positive. And then at 3, it turns around, and the slope is negative. So what does that tell us about our parent graph? It means that up until -1 is concave down. Between -1 and 3 is concave up. And then from 3 onward, it's concave down again. We got a lot of information just from looking at the derivative graph. Now let's go try to answer some of these questions. On what open intervals is f increasing? Well, we just have to look at our picket fence. It's increasing anytime f prime is greater than 0. So between -infinity and a, and between b and c. On what values does f have a local maximum or a local minimum? This is why I love these picket fences, because you can just see what's going on with the graph, right? So we have a local maximum at x equals a and at x equals c, because f prime changes from positive to negative. And then we have a minimum at x equals b, because f prime changes sign from negative to positive. State the inflection points of f and justify. Let's go down to our double derivative picket fence. F of x has points of inflection at -1 and 3, because f double prime equals 0 at these points, and because concavity changes. So f of x is concave up on -1 to 3, f double prime is greater than 0 there, and f of x is concave down from -infinity to -1 and 3 to infinity, because f double prime of x is less than 0 there. So actually, to justify points of inflection, you would need all of these statements. Okay, so what is our graph, our parent graph that we've been talking about? What might it look like? Assume that f of 0 equals 0. Sketch a graph. Well, let's put some points on that we know about. We know that A is a maximum of some sort. We know that B is a minimum of some sort. And C is another maximum. We also know at -1, there's an inflection point, and at 3, there's another inflection point. And now you just kind of have to connect the dots.